Then we elaborated further and looked into biophysical modeling of single neurons, right, where you can model separate parts of neurons. So after that, we again began stepping down to discuss less detailed models, beginning with Fujio Naguma, which is a simplified version of the Hodgkin-Huxley model. Then we looked at Morris-Likar and then ENIAC PK, right, model, which is also a simplified two-variable model. Then we looked at, so these three are limit cycle models. So you try to model action potentials using limit cycles. Then we looked at a few Izikevich models. Right, one of them is a two-variable model, which is very comprehensive, can explain a wide variety of neural firing behaviors and so on. Then we also looked at a quadratic integrated fire neuron model and leaky integrated fire neuron model. So quadratic is obviously quadratic in nonlinearity, and leaky integrate is linear. But these are spike neuron models, so because they have a important resetting step. Then, so these are all, so these three are spike neuron models. Then we looked at dynamic binary neuron model, which is a rate-coded model. So it is rate-coded, but the neuron state is time varying, even for a constant input. Then finally, at the end of this long series of single neuron models, we looked at something called McCullough and Pitts neuron model, which has a simple nonlinearity like a step function. Right now, we will talk about how you can construct network models, neural network models out of this simplest McCullough and Pitts neuron model. In fact, this was the neuron model that triggered the whole, that is the base of the whole neural network revolution. It began in the 40s in some sense, but some follow-up work took place in the 60s, but the real breakthroughs happened in the 80s. Right, let us look at some of those models, and then we'll also look at how all that effort has led to the deep network evolution, and finally we'll see how deep networks can be used to explain sensory function, particularly in visual and auditory domains. So let us look at McCullough and Pitts neuron model. So this neuron model proposed by McCullough and Pitts, McCullough was I think is a psychologist and Pitts is a mathematician who was his postdoc. So they proposed this model way back in 1943, right? And in this, the neuron is like a switching element, right? If the input to it is greater than a threshold, the neuron goes into excited state. Otherwise, it remains in the resting state. So that can be seen like this. So this we have already seen, right? A neuron gets inputs from many other neurons. These inputs are x1, x2, xi, xn, and so on up to xn. They go through a bunch of weights, and then the weights are summed like this, and the difference is called the bias term, right? Or also called threshold term. This whole expression is passed to a nonlinear function g, right? G is typically a step function. Oops. There must be right, or a smooth version of it called sigmoid function. So we have seen these functions in the last class, where we talked about 4 different functions. 2 of them are called hard limiting, have a hard limiting nonlinearity, where you use either a signum function or a step function, and there's a discontinuity at the origin in both these cases. Then we also used 2 smoother versions of them. If the model is following a 0-1 convention, then the smoother version is the sigmoid function, which is also called the logistic function. If it follows the 1-1 convention, then you use tanh function. Okay, so that was the kind of model that McCullough and Pitts proposed, and in fact, in the original McCullough and Pitts model, they use a step function. So there's only one case. All the others are later developments. So they thought that brain is like a computer, and therefore this idea of binary neuron comes from there, is inspired from there, right? And they thought that neurons are like logic gates, right? So therefore, brain is like a big network of logic gates, which is what a computer is, at least conceptually. Since the McCullough and Pitts neurons are binary units, it seemed that it is nice if you can show that the neurons can perform logic gates. Then their insight will be justified, right? So they showed that the McCullough and Pitts neuron can implement basic logic gates, that is and, or, and not, right? Just by proper choice of the weights. So you can see that. Okay, the sigma is the same as the step function here. So if you take this expression, right, which is a special case of the McCullough and Pitts neuron model, because in this case here, W1, so is supposed to be here, which is 1, and which is also equal to W2, which is supposed to be here. And the bias value B is 0.5. Okay, so if you take a special case of a neuron with only 2 inputs, right, and 1 output, and 2 inputs are x1 and x2, and so the weights are W1 and W2. So bias is shown as like a side input, and then output is y. So if you take a simple neuron model like this, then let W1 is equal to 1, W2 is equal to also 1, and bias is 0.1. Then you can see what happens to this. So this is the truth table of the OR gate. This, right? 0, 0 gives you 0, 0, 1 gives you 1, 1, 0 gives 1, 1, 1 also gives 1. So if you plug this in here, if you put 0 and 0, this whole thing is minus 0.5. So pass it through a step function, you get 0. If you put 0 and 1 or 1 and 0, you get 1 minus 0.5, that will be 0.5. So pass through a step function, it is 1. So it's correct. So you can easily verify that this expression satisfies the entire truth table. So okay, so with these weight values, this particular neuron model behaves like the OR gate. Similarly, you can show that if you have slightly different weight values. So in this case, again, W1 is equal to 1, which is equal to W2. But B is 1.5 instead of 0.5. So then what happens is only when both are 0, again, the argument is negative. Even if one of them is 1, the argument is negative because this is more than 1. Only when both are ones, right, this argument is positive. So that's when y will be equal to 1. So it satisfies the truth table of the AND gate. Okay, so and then the NOT gate is very easy because just minus x plus 0.5. If x is 0, the argument is 1, so therefore output is 1. If x is 1, argument is negative, therefore output is 0. So it's a very simple case. So the argument is, so you can think of the neuron as this kind of a threshold unit, right, which takes a weighted sum of the inputs coming from other neurons and computes a binary output. And using such neurons, you can construct basic logic gates. So you can construct any complicated Boolean function using such neurons. So therefore, brain is like a computer. So that was their idea. And it is well justified to think on those lines because this was in the 1943 is when they published their paper. And just around the time, the ideas of computers were becoming quite popular, and all that came to a head, came to some kind of a grand consummation when, in the wake of the Second World War, US built this large computer called the ENIAC, Electronic Numerical Integrator and Computer. This is somewhere in Maryland. So these computers were very large and clunky and of very low power compared to modern computers. When they were using them to calculate, ballistics, that is missile trajectories and things like that. So they could really see the power of the computer. I mean, such a complex machine doing lots of computations and so on. And all that is driven by this Boolean logic and Boolean circuits. So it is natural to think of the computer as a template, right, for brain, and to think of brain as a computer. So it seemed quite reasonable at first glance. But actually, if you look at some closer data, right, some more other data about the brain more closely, you see that kind of a comparison is not tenable, right? It cannot be a good theory of the brain. What is the data? Let us see that. So computer has inorganic 2D sheets of matter. I mean, if you look at the actual circuit boards inside the computer, these are like 2D sheets of matter. Particularly if you see the single microchip is a modern microchip, because the ENIAC computer, I believe, is made up of vacuum tubes and things like that. So it's really clunky. But modern computers have microchips, and these are like 2D sheets of semiconductor material. Whereas brain is a soft organic 3D tissue. But then again, even brain, if you look at it closely, it is made up of layers of neuronal layers of tissue. But anyway, it's a soft tissue. Then computer is powered by DC mains. But with although the original mains is AC, once you go into the electronic circuit, it is converted to DC, right? And some kind of 5 volts or some low voltage is supplied as in DC form to the circuits. Whereas the brain, because it's a live matter, it's tissue basically having a bunch of cells. It is powered by ATP, and its ATP comes from the glucose and oxygen supplied by the blood flow. And ATP is everywhere, right? In every cell. So that's one thing. So then if you look at the signal in the brain, in the computer, so whatever be the uh, DC voltage, right? I just call this VCC. So the distance is a digital signal. It simply goes from either VCC to 0 or VCC to minus VCC. So that is like a digital signal, okay, of amplitude VCC. But in case of the brain, the signal is not a DC. It is not a digital signal. It's like a pulse signal of this form, and the pulse amplitude is roughly 100 millivolts. Okay, and the pulse duration is roughly 1 millisecond. Although this is not like the same for all species, 1 millisecond is a typical figure, for say human neurons. Incidentally, I don't know if you've heard, even plants have action potentials. Only thing is, these are very slow action potentials. A plant action potential can have a duration of about a couple of seconds. So it's a very slow wave. It's not much talked about, because plant electrophysiology is not a very popular thing. There are only few papers, and in the 80s became popular. Although Indian physicist and biologist Jagdish Chandra Bose has worked at a lot of details of plant electrophysiology. So plant has a very elaborate, you can say it's a kind of nervous system. So now another thing about computer is extreme sensitivity to faults, right? That is any dust, you might have seen these days, for example, in IIT we have a lot of air-conditioned computer rooms, but when I joined 20 years ago, it was lots of rooms didn't have AC, and there was a lot of problem of dust. And suddenly the computer stops working because there's a lot of dust in the chassis. And so people would come and clean the dust, and then the computer would work. So that is so sensitive to faults. It will develop loose contacts and stuff like that. Whereas brain is pretty fault tolerant. So in the extreme case, to show the fault tolerance of the brain, right, you can mention this chap called Phineas Gage. So you can look up the story of Phineas Gage. This guy lived in the late 19th century in the US. He was a railroad construction worker. So he was working on a railroad, and his job is to kind of put explosives in the ground and blow up rock. Okay, so to make way for the railroads. This guy was doing that, and once the explosives, blew up prematurely, and the crowbar with which he was packing the explosive inside the ground, it went through his head and went through his eyes and came out from the other side of the head. It's a pretty gory accident, and the thing is, so they had to remove a part of the frontal lobe of that patient, and he survived that accident, right? Which was a big revelation for the entire, world of neuroscience, because even with such a grievous injury, right, to the brain, somebody could survive and brain could work. So it shows how fault tolerant the brain is. Whereas a computer, imagine driving a crowbar through the mainframe of your computer and see what happens, right? So end of story with the computer. So that is one thing that really distinguishes computer from the brain: extreme fault tolerance. Then again, in the computer, you have the clock speeds are very high. The clock cycle is like about nanosecond, order of nanosecond. Whereas the brain, single units are very slow, right? Millisecond is the pulse duration of the action potential. But brain makes up for this loss by using a lot of units. For example, if you look at a parallel computer, which has lots of, for example, you look at multi-core, right? You talk about a few hundreds of cores and the most things like that. In fact, one of the largest parallel computers that I have heard is called a connection machine. This came in the early 90s, and which had like about 64,000 processors. Okay, so whereas the number of processors, if you think of neurons as a processor, and the number of neurons in the brain is, these two figures cannot even be compared. It's 100 billion. So 100 billion neurons in the brain. So whereas in the highest parallel computer will have like a few thousand processors. Okay, you can argue that the single processor is much more powerful than a single neuron, but even that is arguable, because if you take a single neuron with all the dendritic arbor, it can be quite show very complex computations. So I didn't discuss all that in this course. Where brain loses in terms of speeds, it makes up in terms of achieving high parallelism by using a large number of units. Even single units are very complicated. So another thing about our computer is it has centralized clock, right? All the signals in the computer run, they kind of ride over at the centralized clock, which coordinates the signals and synchronizes them. Whereas there's no such centralized clock in the brain, on which all signals ride. They seem to synchronize and desynchronize transiently based on the problem at hand, based on the context. So, which is very dynamic synchronization, and so without any centralized clock. There is a centralized unit. You can think of thalamus as a centralized unit, but then it doesn't work anything like the clock in a computer. Okay, so yeah. So then the next thing is power dissipation in the computer is much higher. This is at level of single bit, 10⁻⁵ watts, whereas in a brain it is much smaller, 10⁻⁻12 watts. So with these differences, so there's one more difference which I'll mention, not they're shown in the table, which is computer is programmed. So you have to tell it what to do. Whereas brain learns from experience, right? From examples, by observing the behavior of other brains or other people, right, or other agents. So that is something that a computer cannot do. At least traditional computer cannot do. With AI now, since you are trying to emulate brain, the computers are also evolving. But otherwise, traditionally, if you compare computer and brain, there's some really fundamental differences. The most basic important differences are extreme sensitivity to faults, right? Whereas very fault tolerant. Programmable versus learning. Second thing is extremely high parallelism, 100 billion neurons versus a few thousand, processors. So these three are very fundamental and very different features between computer and the brain. So therefore, to think of brain as a big computer, as a big logic circuit is kind of tangential. It's not. It's off the target. So for about 20 years, not much has happened, and there's no challenge to that idea. But whereas in the 60s, this guy called Frank Rosenblatt, right? Frank Rosenblatt had shown how you can use the same neuron model that was proposed by McCullough and Pitts and make it learn. So instead of programming it like a logic gate and connecting and configuring Boolean circuits, you can make this neuron learn something. Okay, so let us see how it works. So you can take a neuron like this, right, and you can make it learn to classify some patterns. So the input is a vector x. It gives you some output. Now the output y, right, can classify the pattern. Let us the simplest case is x is either in one of two possible classes. X is in either class 1 or x is in class 2. So now you can make this single neuron, right, classify x and say whether it belongs to class 1 or class 2, right? If it is in class 1, let us say y is 1. If it is class 2, let us say y is equal to 0. So a single neuron in principle can classify an input vector into two classes. If you want more classes, then you have to have more neurons, but we'll come to that later. So now the question is, if I give an input x and how do I make the neuron classify the input appropriately? Because initially the weights are random. In case of logic gates, we have just inspected the problem and then kind of somehow guessed the weight values just intuitively because it's a very simple problem. But in general, you cannot just intuitively guess the weight. So there must be some kind of an algorithm or some procedure, right, for finding the weights. And how do you do that? So for that, the general scheme or approach is like this. So think of this as a neuron, and we'll replace it with a new network of neurons later on, increasingly larger and larger networks of neurons. But the schematic is the same, no matter whether you have a single neuron or a large network inside this box. So this network basically takes an input vector x and produces an output y. And we want the y to be equal to something, right? And so that is the target output t, right? Sometimes you also use a notation d, which represents desired output. right? And so the compare t and y, so that is t minus y. You get the error between the target and the desired. So the target and the actual. Then pass this error to the neuron or to the neural network, and there are certain learning rules which will let you update all the weights inside this box. Because as you keep on updating the weights, the neuron will try to produce the correct response for a given input. But the output is, continues to or proceeds to look more and more like the desired output or target output as the network is trained. So in this case, the weight update is the weight learning is like this. So let me derive that. So take this single neuron. It takes inputs from many other neurons. So inputs are x1, xi, and xn, and so on. Output is y, and y, as you know, is given by this function g of sigma wi xi minus b or theta. Okay, so how do you find the correct weights and b? So this is the question. Okay, so what do you mean by finding the correct weights and the bias term? That is, what are the weights that will make sure that for every input x, you have two things. I'll have input x, then I have the desired output d, and then I have the actual output y. Okay, so in this case, let's take a very simple case. X is a vector in Rn, whereas both d and y we assume to be not only real numbers but equal to just 1 or 0. Simple binary values. Okay. Now, so you'll have to take a training data set. So where you have a bunch of vectors x and the corresponding values of d is something like this. This is a kind of a data set we had in case of logic gates. So, for example, your truth table for each logic gate, you can think of it as a training data set. Take some examples like that and give the corresponding desired outputs. Now, if the network is working well, so ideally, y should be equal to d. Okay, so this is ideal, right? So this is what the weight should give me. But in general, when you started, when you randomly initialize the weights, so y will not be equal to d. So the objective of learning is to make y equal to d. So how do you capture that? So I'll define some kind of an error function as d minus y, okay, square, so that now when y equal to d, this error function goes to 0. I'll put a half here, and I'll sum this over p, where p is the index over patterns. So these are the patterns, right? These are the input patterns, these are the output patterns, but these are the patterns in the training data set. So the index is the index over this pattern. So I take an index over that, loop over that, and add up all the errors, the squared errors. And I want this to be, ideally, if it is 0, then for every case d is equal to y. In general, that may not be the case. So the question now is minimize. I use the symbol e. Minimize e, right? And what is the wi and b such that e is minimized? So this is the problem. So for this, we do something called a gradient descent. So that is, so e here is a function of wi and b. So what are the values w and b which minimizes e? So for that, so normally we are used to minimizing functions by simply taking the second derivative. But thing is, that kind of an approach may not be. So you can just do like del e as a function of w and b and just set it to 0 and solve it. Okay, so that might work for simple functions, but if you have a large neural network, this will not work because you can't have an analytic solution for this equation. So people depend upon an iterative solution. Okay, so analytic solution may not be possible, not always possible. So we depend on iterative solution. So how do we do that? So this is E, and this I'll just check to be some parameter W, right? Wi. So let us say the function becomes minimum at this value of Wi, and we need to find out what that is. And initially I'm somewhere here, far from that. So we can't jump from here to here in one shot, but we'll move towards it in small steps. So if I'm here, I have to move towards the left, and if I'm here, I have to move towards the right. How do I know that? So if you look at the derivative here, the derivative here is negative, and I want to move to the right. And derivative here is positive, and I have to move to the left. So moving to the right means increasing W, and moving to the left means decreasing W. So which means when this derivative is negative, you have increasing W, and when derivative is positive, you are decreasing W. So this can be captured simply as a learning rule like this. But delta W is proportional to the negative of the derivative, which is delta E with respect to W. Or you can take it as, so this is true for for the entire vector. So you can take delta W as a vector, which is equal to minus del of E with respect to W. So similarly, you can say delta B also is proportional to minus dou E by dou B. So if you do that, you get some simple expressions. So we'll look at them later. So this kind of an approach is called gradient descent. So we'll use this method not just for a single neuron, but even for a very complicated large network models. So we'll visit that equation, we'll visit this concept again, and then derive the actual equations later. Now the Macaulay-Pitts neuron, let us see what exactly it is doing, right? So when the argument here, if it is negative, output is y is 0, right? And sometimes people use notation net. So net is defined as is equal to the sigma wi xi minus b. So if net is less than 0, y is 0. Net is greater than 0, y is 1. So it's a step function. So when it is net less than 0, there's a whole set of input space for a lot of x vectors x, right? Net is less than 0. For a lot of vectors x and net is y greater than 0. So then what is the shape of these two regions, right? The set of all points for which this is true and set of all points where this is true. Right? What do these sets look like, and what is their boundary? At what point do you go from this region to this region? So you can see that on the boundary, right, this has to be equal to 0. So if you solve for this, you get a straight line. And on one side of the straight line, this expression will be positive because it's a linear expression. And everywhere there, y equal to 1. Other side, y is equal to 0. So basically, the Macaulay-Pitts neurons, because of the weights, it divides input space into two semi-infinite halves. And that way it can classify the input into one of these two classes. So let us see how you can use the perceptron to learn and to train it on this very simple problem. So earlier we solved the logic gate, NOR gate, and we just found out what the weight should be like, right, by inspection. Now let us train a neuron and to make it behave like a logic gate. So this is the truth table of the logic gate. So this is our training set. Okay, now how do you train this? So initially I take some random weights, let's say 0.2, 0.3, and p is equal to minus 0.2. So for these parameters, this is called the decision boundary, right? The decision boundary where is like this. And for these values of the parameter, the decision boundary is here. And so the 4 points are here. So there is This is one here. So this is, so the points where the output is 0, right, is indicated by a circle, and points where output is 1 is indicated by an X. Okay. So the decision boundary is way off. Ideally, what you want is a decision boundary which goes something like this, so that on one side you have all the points where y equal to 1, other side you have only one point, that is y equal to 0. But the association boundary for the initial random parameter is totally off. Right, let us see what happens. So you present, so first you present 0, 0. Okay, this is wrongly classified because this line should be somewhere here. So this is on the wrong side of the data point. It's wrongly classified. So you update the weights using this, using certain rule. And so then you present, so that update gives you these new weights. Then you present 0, 1 is correctly classified. When it's correctly classified, the weights don't change. Then present 1, 0 is also correctly classified. So therefore weights don't change. Again present 1, 1 correctly classified, the weights don't change. Okay, so out of 4 data points, it correctly classified 3 data points. So accuracy is 75%. Okay, but still that's not 100%, so you have to go over them again. So again present first point, 0, 0. Okay, now it is wrongly classified. So you have to update the weights, right? And because of that, the weight suddenly jumped to this point. Okay, so you see that so these are the 3 points where y equal to 1, and this is the point where y equal to 0. So the line suddenly jumped from here to here. Okay, and now once you have this, you're okay. So this you have correct answer because at these 3 points are on the positive side of this line. So here y is equal to 1. Here it's negative side. So it's giving correct results. So now you will find that for all the patterns you get correct classification. Okay, and therefore it's completely trained. So what you can see from the simple example is there is no unique solution to the problem because any of these lines going through the space like this, okay, would have worked, right? So in this iterative search for a correct solution, the network might find any of these lines, and once it finds that, it stops. You get 100%. So it's so thing is, unlike in a programmed approach to problem solving, you have to find the correct set of rules and you have to program the computer to do exactly that. But you see, in a neural network, the exact weights that it will learn is not in your control. It will reach somewhere, and that some set of weight parameters will give you a correct solution, and that's it. It's like some kind of a creative solution generation, right? That's what the neural network exhibits. It finds a solution on its own in some sense, a creative fashion. But the problem with this model is it can only separate the two classes, right? Only with a straight line. This is a 2D case, so it's a straight line. Otherwise, it's in general it's a hyperplane because if x is an n-dimensional vector, then this equation will define an n-1 dimensional hyperplane. So it can classify the two data sets only when the two data sets can be separable by a hyperplane, or since its hyperplane is a linear hyperplane, you say that the two data sets must be linearly separable. Okay, otherwise it cannot classify the two patterns. So suppose you have data like this, right? The blue dots are one class, and the green little circles or whatever are the other class. So no matter where you draw your line, right, it won't be able to separate the blues from the greens. But if you are allowed to draw a kind of a curve instead of a straight line, right, you can separate the blues from the greens. But as far as this neuron is concerned, you can only draw straight lines. It can only draw planes. So it won't be able to separate this. So one nice thing about this kind of Machiavellian neuron, in fact, it is when you use in network form, we call it a perceptron. But that was a term given by Frank Rosenblatt. Right? In case of a perceptron, it can classify patterns, it can learn on its own. These are nice things about it. But it can classify the patterns only if they are linearly separable. Right? That means there must be a hyperplane, there must exist a hyperplane. which can separate those classes. Only then this neuron or this network can learn those classes. Right? So that's a big kind of disadvantage. And another thing is when they are linearly separable, right? You can have infinite number of solutions, so therefore solution is not unique, which is okay. It's not a problem. It's just a property of the perceptron. Now, because of this limitation that it can only classify linearly separable data, it can learn the three basic logic gates, that is AND, OR, and NOT. Because all these three cases, you can think of it as a classification problem because output has only two values, 1 or 0. Okay, so it's a two-class problem. In all these cases, the data is linearly separable. Okay, so therefore the McCullough pitch neuron model can learn this. But if you take another logic gate, which is XOR gate, the truth table of it is given by this. So 0, 0 is 0, 0, 1 is 1, 1, 1 is 0, 1, 0 is 1. Okay, so 0, 0 is 0 and 1, 1 is also 0. So these opposite points are in one class, but 1, 0 and 0, 1 are in another class. So no matter how you draw a straight line, you can never separate the blues and the greens, right? So if you try to learn this logic gate, so this XOR gate, that using a single McCullough-Pitts neuron or the perceptron with single neuron, it won't be able to learn this. So this was a big drawback, and there was need to improve this, right? And I'll stop here. I'll let you think on these concepts, and I'll derive the perceptron learning rule in the next class, and then we'll show that when you go to a higher multi-layer version of this, you can make this problem go away, and you can show that the network can learn much wider class of problems. So thanks a lot. See you tomorrow.